A solenoid with a resistance of 5 ohm and an inductance of 5 millihenry is connected to a 12 volt 50 Hz AC supply. So let's draw it up. You have a solenoid. Okay, then it mentions here that this solenoid has a resistance of 5 ohm. Well, some of you might be thinking, usually when we talk about solenoid, why we talk about inductance only? Usually just inductance L equals to 5 millihenry. So why is there a resistance for this case? Well, actually, most of the solenoid that you deal in chapter 5 are actually ideal solenoid. So ideal solenoid are like solenoid with pure L. There's only inductance, there's no resistance. But if you think about it, it's actually quite impossible because solenoid are made of wires. And if you coil it into a solenoid, then the length will be very, very long actually. If you unwind it, it should be very, very long. So if the length of the wire is very, very long, you should expect that there's some resistance to the solenoid, right? So actually in real life inductor, there's actually some form of resistance inside it as well. Okay, and in this case for this solenoid, even though it's an inductor, it also has a resistance of 5 ohm. Okay, and then you connect it to a 12 volt 50 Hz AC supply. Okay, so let's connect it up. Probably connect it something like this. Then this is our AC supply, and this AC supply here supplies 12 volt. They didn't mention its peak, so it must be root mean square 12 volt. Then also they tell you that it's 50 Hz frequency, so the oscillating voltage here is oscillating at 50 oscillations per second. Okay, so now they ask for what is the impedance in the circuit. Well, when they ask about impedance, let's try to do it the formal way and bring back the formula that we learned here. So we are finding impedance, so it should be this formula over here. This formula over here. You are taking R square plus the inductive reactance minus the capacitive reactance square. Okay, so we'll be using this formula over here to try and determine it. Okay, so Z should be equals to R square plus, you can write it this way first, write the inductive reactance minus the capacitive reactance. You can write it like this first, then slowly you break it open. So for R, I think we have it. For XC, XL, we can find it. For XC, I believe it's 0. Okay, for XC it should be 0 because there's no capacitor over here. So let's break it one more step further, then plus, then this will be omega L. But instead of writing omega, let's try write it as 2 pi f. Okay, then we can save some lines. 2 pi f inductance minus 0 because there's no capacitance. So now it's a matter of substitution again. So our resistance is 5.0. Then you square it, then plus, then you have 2 pi times the frequency is 50 Hz, just like our normal power supply, and our inductance is 5 times 10 to the power of -3. So close it up, square. So if you calculate all these things over here, I believe you should get an impedance of 5.24. Again, the unit is ohm because it's also a ratio of V0 to I0. Okay, so that's the impedance. Next step, they ask for the phase difference between the voltage and the current. So in order to obtain the phase difference, we know that it involves something called tangent phi. And we know tangent phi here can have a few different versions. You can take the peak current here for the inductor minus the peak current for the capacitor divided by the peak current for the resistor. But if you look over here, there's no info on the peak voltage for L, C, or R. So I believe it's another version. There's also an RMS version, but I don't bother to write it down because you know that wouldn't work either. There's also another version which is XL minus XC divided by the resistance. This equation here is obtained by factorizing out the current, the peak current, then simplifying it off, then you're left with basically just the reactance and the resistance. Okay, so this formula might work. Let's try it out. So phi here, the phase angle should be inverse tangent of XL. XL here is 2 pi frequency times inductance, and then we know that XC is equal to 0, then divide by the resistance R. So I believe you can now start to do substitution. Then it will be inverse tangent of 2 pi 50 hertz. Inductance is 5 times 10 to the power of negative 3. Then you divide by the resistance. The resistance here is 5 volt. So if you calculate everything here, I believe you get an angle of 17.4 degree. 17.4 degree here, it's positive, so you can think of it as the V is actually leading the I. So V leads I. You can write it here, okay, but they didn't really ask for it. But you can just write V leads I, then the phase angle is 17.4 degree. Okay. And then the last thing they ask is what is the RMS current? Well, you know the VRMS already, and they want the RMS current. You know that VRMS and IRMS, they can form a ratio which is equals to Z. Okay, so you know Z, you know VRMS. I think IRMS should not be a problem. So this should be root mean square voltage divided by Z. Again, this root mean square voltage over here is the root mean square voltage across the whole circuit. So if you want to measure it, you probably have to measure it by connecting a voltmeter over here. Okay, of course you can also connect it over here, should be fine as well. Okay, anywhere, as long as you are connecting to measure how much is the potential difference across the whole circuit, then you are fine. Okay, so let's continue and try to determine this. So VRMS, we know that it's 12 volt. Then the impedance we learned from just now is 5.24. So from here, if you do our calculation, we find that our IRMS current to be equals to 2.29, and the unit should be ampere. Okay, so definitely the formula will make things a bit easier for you because yeah, it's just direct substitution. But I hope you all can remember the essence of this formula, because this formula is obtained just by Pythagoras theorem with the x component of the phasor diagram and the y component of the phasor diagram. This part is also the y component of the phasor diagram divided by the x component of the phasor diagram. So these are helping you to remember how the formula should look like in case you forget whether it should be a plus or a minus. Okay, knowing where it comes from can be very, very important. Okay, so that's all for this question.